So in this lecture, I will discuss regular conditional probability. So throughout the lecture, we will have a space, probability space, a set omega sigma algebra F and a probability P, and a sub-sigma algebra G, which is contained in F. So let me remind you about conditional probability. So if we take A subset in F, we represent by P A given G the conditional probability of A given G. So this is, in terms of the conditional expectation, the conditional expectation of the indicator of A given G. And so it's a function from omega to 0, 1, which has the following properties. First, it is G measurable. And second, for all sets B in G, the integral over the set B of this conditional probability it's equal to the probability of the intersection. And we have seen that, so these are exactly the properties of the conditional expectation of the indicator function A given G, and we have seen that there exists a unique up to almost surely relations. There is a unique probability, conditional probability. So I will represent this function by the symbol in this lecture mu lambda omega A. So mu given A, mu dot A, so it's the function which goes from omega to 0, 1. And this function, therefore, has two properties. It's first a G measurable function, and second, so let me rewrite this identity in terms of this newly introduced object. So in terms of this notation, this means that the integral of mu dot A dp, so here, this is a function of omega. I'm integrating this function with respect to P over the set B, and this relation tells me that this is equal to the probability of A intersection B for all sets B in G. So I'm representing in this lecture this probability as with this notation. And I will first extract some properties of this object for to define later what is the regular conditional probability. So I just rewrote the notation I just introduced. So I'm representing this conditional probability by this notation. And these are the two properties which characterize this conditional probability. So now I'll make some remarks. The first one, they are all very elementary. So if I take the set A to be omega, then what I claim is that mu omega, it's equal to 1 almost everywhere. And maybe I'll leave to you to check this as an exercise, but what I'm claiming is that if you take A equal to the whole set omega, then this function, it's almost surely equal to 1. And in the same way, if I take A to be the empty set, then mu of omega of the empty set, that this is equal to 0 almost everywhere. Mind that these are two distinct functions. So for each set A, I have a function from omega to 0, 1, which is G measurable. So my second remark is that for all B in F, this function, it's a function which is less or equal than 1 and larger or equal to 0 almost everywhere. This is also pretty clear. And the third property is that now if I take a sequence of sets bj, say that bj belongs to F for all j larger than 1, and that they are 2 by 2 disjoint. So if I take I different from j, this intersection, it's equal to the empty set for I different from j. And then what I claim is that, well, you have a function which is associated to the union of these sets. So the union, this is a new set, and this gives rise to a new function, which is represented by this object. And what I claim is that this is equal to the sum of the functions associated to the sets bj. And this, of course, holds also almost everywhere. So I leave it to you to check these three properties, but my observation is that whenever I say that some identity or some inequality is true almost everywhere, this means that there exists a set n, which is an element. So let's, for instance, write down what this identity equal to this object equal to that one almost everywhere means. This means that there exists a set n, which is G measurable. Its measure with respect to P, it's equal to 0. And for all omega, which does not belong to this null set, then this identity holds for omega. This means that mu of omega it's equal to the sum of mu omega bj. So this is the meaning of this sentence, that this is equal to that almost everywhere. So that means that there exists a set. Mind that this set is in G, because those two functions are G measurable. So there exists a set in G which has measure 0, and such that this identity holds for all omega which do not belong to this set n. The problem here is that for any, if I replace this family bj by another family aj, say, we get another identity which holds almost everywhere, but the set on which it holds is different. And since they are an uncountable family of relations, if I take the union over this, of these null sets over an uncountable family, I get something which might not be measurable and which might, whose measure might be different from 0. So the problem is this one. We would like to have a unique null set in which all these relations which hold outside of it. And this is the goal of constructing this regular conditional probability. This means that to have a unique null set, so a set which is G measurable and whose measure is equal to 0, and which the property that if I take an omega which doesn't belong to the set, then all these relations which will hold for these omegas. So whatever family bj I get in F, this identity will hold, and all other relations I can imagine will hold in the complement of this null set. So this will be the goal of this lecture. So let me define the object which I want. So this will be the definition of a regular conditional probability. That will be a function, mu, which is defined on omega times f. So remember, f, it's the sigma algebra. So remember here, we had this function mu defined on omega and a, for a in f. So mu, it's a function from omega in f, taking values in 0, 1. And with the following two properties. The first one is that for all omega in omega, mu omega as a function of the second coordinate, which is defined in f, is a probability measure. So I want that for all omega fixed, as a function of the second coordinate, this is a probability measure which is defined on F. So a probability measure defined on the sigma algebra F. And then, well, the second property is that if I look at it as a function of the first coordinate, it is the conditional probability. This means that for all A in F, the function mu dot A is a version of the conditional probability of A given G. So what means that this sentence, it is a version of, it has two sense, 2A. It means that the function omega, which to omega associates mu of omega A, and this is true for all A, this is G measurable. So this is the first property of this conditional probability. We want this function to be G measurable. And the second property, that for all sets B in G, if I integrated over the set B this function mu, so here I have a function which depends on omega. I'm integrating this first variable with respect to P, so that this is equal to P A intersection B. And this holds for all B in G. So I will say that this function mu from omega F to 0, 1 is a regular conditional probability given G. So this is the name of this function. So a regular conditional probability given G if these two property holds, which means that for any fixed omega, if I observe this function as a function of the second variable, this is a probability measure over the sigma algebra F. And secondly, that for all A in F, so if I take any set A which belongs to the sigma algebra F, well, as a function of the first coordinate, this is a version of the conditional probability of A given G, which means that it's a G measurable function, and that for all B in G, we have this identity. So this is the definition. Unfortunately, these regular conditional probability do not exist in general, but in certain cases they do exist. So what I will prove here is that if I take as omega the set, the interval 0, 1, and F as the Borel sigma algebra over these sets, then there exists a regular conditional probability given G, where G is any sub-sigma algebra of B. And the proof will give you a very good idea of how to prove this theorem in a more general context. So the lecture is divided in two steps. First, I will derive a brief consequence of the definition of this regular conditional probability, and then I will restrict myself to this example and prove that in this example there exists a regular conditional probability. So here's the remark. Let me take a function f from omega to r, which is f measurable and which is integrable. With respect to p, that means that f dp is finite. So now what I claim is the following. Well, we know that for any fixed omega, this is a probability measure. So let's take this function f and integrate that with respect to this measure. So mu omega is this measure, which is defined on f. So since f, it's, well, let's say that f it's bounded, then this is well defined. I'm integrating over a probability measure, a bounded function. which is measurable. Both of them are measurable with respect to the same space, same sigma algebra. Mu is defined on F, and I'm assuming here that F is F measurable. And what I claim is that this is a version of the conditional expectation of F given G. So once I have a regular conditional probability, in order to get I can express all conditional expectation in terms of an integral with respect to this regular conditional probability. So this is what I claim, and I claim that this is well defined, provided F is integrable, and moreover, that we have this identity. And how do we prove this claim? We go step by step, as we do usually. So first, we will prove that if F is the indicator function of a set A in F. So let's assume that A belongs to F. Let's consider the indicator function of this set, and let's prove that this identity holds. So on the left-hand side, we have the integral over the indicator of d mu omega. Well, this, by definition of this integral, it's mu omega of A, which is what we are representing by mu omega A. So the measure of the set A with respect to this probability measure, mu omega. So this is the left-hand side, sorry. And on the right-hand side, what we have is that the conditional expectation of F, but when F is the indicator of a set A, given G. So this is the probability, conditional probability of A given G. And, well, and indeed, these two expressions are equal, and this is, of course, almost everywhere. I forgot to insist on this fact. I'm claiming that this identity holds almost everywhere. And indeed, by the second property of mu A, it's a version of this conditional probability, and the right-hand side, it's exactly the conditional probability. Therefore, these two objects are equal, which means that this identity holds almost everywhere, provided F is equal to the indicator of a set. Now, I can extend this identity to simple functions. Just by linearity. All right, so a simple function, remember, it's a function which is written as Cj, the indicator function of a set Aj, for a finite sum. So on the left-hand side, I can use just linearity to remove the sum outside of the expectation, then the constant, and then apply the identity 1 in the case in which F is the indicator of this set. And also on the right-hand side, I can use the linearity of the conditional expectation in order to take out the sum and the constants. So once we proved that this identity holds for the indicator of function, we get that it also holds for simple functions. Then we use the monotone convergence theorem to extend this identity to a function f, which is non-negative. Here, I'm using, on the left-hand side, the usual monotone convergence theorem for integrals, while on the right-hand side, I'm using the one which we proved in the last lecture, so the conditional monotone convergence theorem. So if now I remember that if f is measurable and non-negative, I can always find a sequence of simple functions which increase to f, and then I can use this identity for these simple functions and the monotone convergence theorem to extend this identity to non-negative functions. And the last step is to take a function which is integrable. If this function is integrable, I can always rewrite it as its positive part minus its negative part. Now I can use both of these functions are integrable because f is integrable, and then I can use the linearity of the integral and the linearity of the conditional expectation to extend this third identity to integrable functions just by using linearity. So proceeding in this way, we can prove that indeed, once I have a regular conditional probability given a sigma algebra G, I can express the conditional expectation of any function f as the integral of f with respect to the regular conditional probability. So as I said, regular conditional probability do not exist in general. If the space is too big, they don't exist. But we will prove here a theorem that they exist in the following situation. So let's take the set 0, 1 with the Borel sigma algebra of the set and some probability measure which is defined on this set. Now let me take a sub-sigma algebra G of the Borel sets, and the theorem says that there exists a regular conditional probability given G in this context. So we will construct this function mu of omega A with all the properties required. So the proof is divided in several steps, as usual. And you'll see that the proof is not very difficult. So let me fix x, a rational number x, and let me denote it by ix the interval minus infinity x. Now, let's consider the conditional probability of ix given G. So this is a function from omega, which is 0, 1, to r plus, or 0, 1, which is G measurable, and such that if I take any set B in G, I have that the integral over the set B of this conditional probability this is equal to the probability of B intersection Ix. And this for all sets B in G. So I will represent this function as fx. So that function will be represented by fx of omega. So this is my notation for this conditional probability. So x, it's fixed, is a rational number, and for that given fixed x, fx, it's a function from omega, which means 0, 1, to 0, 1, and this function fx is G measurable and has this property. So let me rewrite this. So fx is G measurable, and the integral over the set B of fx dp, this is equal to the probability of B intersection minus infinity x for all B in G, sorry. So these are the properties which define this function fx. It is G measurable, and it satisfies this identity. So this is my definition of fx. Now for each x, I have a function fx. And with these functions, so I'll first show that, well, I can change fx in such a way that it becomes a distribution function for each x, and therefore I will have a family of distribution functions fx. With this family of distribution functions, as we did in a previous lecture, we will construct one which is a distribution function associated to, well, with this fx we will define a distribution function g. And so let me make more precise. So we have these functions fx, And now I want to, so these fx are defined for x in k. So we will now fix a point omega in 0, 1 in some set, which I will define later. We will fix that omega, and we'll start to consider the function which associated to x, this value fx. And what I claim is that, well, this almost satisfies the condition required to be a distribution function. Right? Well, which means that it's monotone in x, it converges to 1 in plus infinity, it converges to 0 in minus infinity. But mind, fx, it's only defined for rational points x. So as we did in previous lectures, we will now, with these fx, define a new gx, which now it's defined for all x in R, and which is a distribution function. And this we did before, so we'll define gx as the infimum of fx of fy for y larger than x. And in this way, we define gx, and we will show that gx, it's right continuous, it's monotone, converges to 1 in plus infinity, and to 0 in minus infinity. Which means that for omega in some set, for all these omegas, if I fix the omega, what I get is a distribution function. But once I have a distribution function, I can construct a measure, q omega. So this is the measure associated to this distribution function. We have seen that there exists a one-to-one correspondence between distribution functions and measures on R. And this will be our candidate for mu omega. So this is the idea of the proof. So we started by defining these functions fx, which are given by these conditional probabilities. Now the advantage is that we have a set Q, which is dense and countable on R, or on the set 0, 1. And this fact, which is that we have a countable dense family, which will enable us to construct this final measure Q, which is mu in my previous notation. And here what we will do is that, well, we will claim that as a function of x, this is almost distribution function, almost because, well, first fx is not defined for all x, but only for rational numbers. And then, well, because we will have to avoid certain sets of measure zeros in which f, it's not monotone, or it's not 1 at plus infinity and 0 at minus 1, or at minus infinity. But what you have to keep in mind is, for the moment, is just the definition. So I defined for each rational x this function, which is g measurable and which has this property. And now the idea is that, well, here we fixed x and we consider this object as a function of omega. Now what we want is to understand this object in the other way, so that we'll fix omega and observe this as a function of x and try to prove that as a function of x, this is a distribution function in the sense I said, which means that it's, well, it's defined on rational, it's monotone, it's converges to 1 at plus infinity and to 0 at minus infinity. So I recall here the definition of our function fx. I forgot to say that this is defined for x, a rational number. And now let me prove some properties of f. So my first claim is that, well, fx, so this is a function which is g measurable. And what I claim is that this function, it's less or equal than f of y if x is less or equal than y. So that's my first claim. And this is almost obvious, because the random variable minus infinity x it's less or equal than the indicator of minus infinity y, because x it's less or equal than y, then we can use the monotonicity of the conditional expectation to take on both sides the conditional expectation with respect to g. Once we do that, on the left-hand side we have fx, on the right-hand side we have fy, and the monotonicity of the conditional expectation tells us that indeed fx it's less or equal than fy almost everywhere. So this means that, let me represent by nx, y the set on which fy it's less than fx. So this set belongs to G because both fy and fx are G measurable, and the probability of nxy it's equal to 0 because this inequality holds almost everywhere. So this is a first example, so that we will start to discard some sets which have measure 0, and since we are working with a set which is countable, we will be able to discard all of them just because we are taking countable unions of sets of measure 0. So that was my first claim. My second claim is that if I take x smaller than 0, then fx it's equal to 0 almost everywhere. So what I'm saying is that this function fx it's equal to 0 at almost everywhere. So how do we prove that? Well, we know since fx it's a conditional expectation is that fx of a non-negative random variable is that fx it's larger or equal to 0 almost everywhere. Now let's prove that. Let me take the integral over a set B in G of fx. And so let's recall this identity. This is the probability of B intersection minus infinity x. But B it's in G, and so B it's a subset of 0, 1, which is G measurable. And since x is less than 0, this intersection is empty, and therefore the probability of this set it's equal to 0. So this is the probability of the empty set, which is 0. So we have a non-negative function, which is G measurable. So a non-negative function which is G measurable, and with the property that its integral over any set B in G, it's equal to 0. So that implies that indeed fx it's equal to 0 almost everywhere. And that's a simple exercise from measure theory, which I leave it to you. So we know that it's monotone. We know also that fx it's equal to 0 almost everywhere for x smaller than 0. So let me call nx the set of omegas such that fx it's different from 0. And so what we proved is that if x it's less than 0 and a rational number, then nx it's a set in G because fx it's a G measurable, and the probability of nx it's equal to 0. The probability of the set nx it's equal to 0. And finally, my third set, let me write it here. So my third claim is that now if I take x larger or equal to 1, then fx it's equal to 1 almost everywhere. And the argument it's exactly the same. We know on the one hand that fx is less or equal than 1 almost everywhere. And we will prove by this argument that for any set B in G, the integral of fx over the set B, that this is equal to 1. And from these two facts, we can conclude that fx is equal to 1 almost everywhere, and defined exactly in the same way the set nx. So for x larger than 1, nx will be the sets of omega such that fx is different from 1. This set is G measurable and has measure 0. Now we can take the set n, which is the union of all these sets. So n will be the union of x less than 0 of nx, the union of, well, all these sets, all these x are rational numbers. And the union for x less than y, x and y rational numbers of nxy, where nxy is defined here. So if I take n as the union of these three classes of sets, you observe that we are taking a countable union, that all these sets in this countable union have measure 0, which means that n is measurable and its measure it's equal to 0. So the probability of n it's equal to 0. And now I will fix omega, which belongs to the complement of n. So if omega belongs to the complement of n, I have that all these inequalities, all these statements are correct, which means that if omega belongs to the complement of n, fx of omega is bounded by fy of omega is x bounded by y, fx of omega is equal to 1 if x is larger than 1, and fx of omega is equal to 0 if x is smaller than 0. So from now on, I will fix a point omega in the complement of n. I will keep these identities or these statements which which are written here, and from these, as I said, I will now start thinking of this as a function of x. And from that function of x, I will construct a distribution function, and from that distribution function, I will construct a measure on the set 0, 1 and the sigma algebra B. So, in the last take, we construct a set n, which is G measurable and has measure 0. And with the following property, if I take an omega which is not in n, it's in the complement, then for all xy in Q, fx of omega is 0 if x is smaller than 0, fx of omega is 1 if x is larger or equal than 1, and f as a function of x, this function is monotone, so if x is smaller than y, both in rational numbers, then fx is less or equal than fy. Now, from that, we will construct a distribution function, which I will represent by G. So omega is fixed. It's fixed in the complement of n. And observing these as a function of x, I will construct an object which is a distribution function, which means that, which has the following properties. Well, in our case, okay, so the properties are that the limit as x goes to infinity of gx of omega is 1. As x goes to minus infinity, the limit is 0. Then that it's right continuous, this function is right continuous, and it's monotone. So the difference from G to F is that G now will be defined for all x, and it will, since it's defined for all x, it makes sense. Well, it would make sense also, but while I did not guarantee that this function is right continuous, G will be right continuous. So, so the second step consists in constructing these distribution function, G. And we will proceed exactly as we did when proving that the space of distribution function is compact in the, for the weak topology. So the definition, remember, omega is fixed. So the definition of gx, now x is a real number, will be to take the infimum of fy of omega, such that y, well, this is defined only if y is a rational number and if y is larger than x. So define gx in this way. We can drop from the notation omega because omega is fixed. The only thing we need to do is to use these three properties. And what I claim, and I leave it to you to check, is that first, gx of omega it's equal to 0 if x is less than 0. All these properties are elementary consequences of these three inequalities, and if you want to see a proof, you go back to the result I just mentioned. Then I claim that gx of omega it's equal to 1 if x is larger or equal than 1. It's monotone, so if x is less or equal than y, this means that gx of omega it's less or equal than gy of omega, and it's right continuous in the sense that gx of omega it's equal to the limit as y decrease to x of gy of omega. Okay, so I claim that these four properties follow from these three conditions. I leave it to you to check that they all hold. And this means that as a function of x, gx of omega, it's a distribution function. And we have seen that there is a one-to-one correspondence between distribution functions and measures. And so I will represent by q of omega the measure which is associated to gx. So what did we do in this second step? We started from a point in the complement of n, and we proved that we construct a distribution function with, by this equation. So we define this function, we prove that it's a distribution function, and since it's a distribution function, there is a measure associated to it, q, and so q omega is the measure on 0, 1 Borel, which is associated to this distribution function g. Mind, before we go to the next step, is that this function gx, so for all x, gx, now as a function of omega, is g measurable. And why is that true? Well, because these functions, fy, are monotone. So this limit is actually the limit as y decrease to x, y taking rational values, y is strictly larger than x, of fy. And fy, we have seen, are g measurable. So if we take the limit of a sequence of g measurable functions, the limit is g measurable. So this means that indeed, for all x in R, gx is g measurable. So now we will prove some properties of gx and of this measure q from this definition of gx. So what you have to keep in mind now is that we defined this gx by this formula. Gx is measurable, it's a distribution function, and represented by q, the measure on 0, 1b associated to this distribution function. Well, so now step 3, we constructed this measure Q of omega, and this for omega in the complement of n. So this is our candidate for the regular conditional probability mu. So I recall here the properties of the regular conditional probability. We need that for all omega, mu of omega, it's a probability measure. That's nice because, well, up to now, for all omega in the complement of n, Q of omega is a probability measure, so by our construction. Of course, for the moment, Q, it's only defined in n complement, so let me take omega in n, and this is a set of measure 0. So in this set of measure 0, I will define Q in any way. So maybe Q of omega, if omega belongs to the set n, will be just the Lebesgue measure. So L is the Lebesgue measure defined in 0, 1. And let me set Q of omega to be this measure if omega is in n. Now, we have the first property. The first property is matched. For any omega, Q of omega, it's indeed a probability measure defined on 0, 1 with the Borel sigma algebra. So the first property holds. What remains to be done is to prove the second property, which is divided in two pieces. First, we have to show that for any fixed a as a function of omega, this is a G measurable function, and then that we have an identity. So my question here will be now to prove 2a. So my claim is that for all a in F, Q omega a, which is the measure. So for each omega, we constructed a measure Q of omega, and we are taking Q of omega of a, so that this function, as a function of omega, is G measurable. So this is what I need to prove. So let's prove that. Well, we will prove that in step by step. So we will first show that this is indeed true if a is equal to minus infinity x. So I claim that if a is equal to minus infinity x, then indeed Q omega of a is G measurable. But that's obvious because this is equal. Here we are taking the measure of the set minus infinity x. So this is exactly equal to the distribution function computed at x. But the distribution function associated to Q, it's G. So this is equal to Gx of omega. And we have seen that Gx is G measurable. So this is equal to Gx if omega belongs to n complement, and it's equal to, let me call maybe Lebesgue, so Lx of omega. So let me call by Lx the distribution function of the Lebesgue measure. So L of x. So L, mind, is the distribution function associated to the Lebesgue measure. So it's equal to 0 up to 0. Then it's constant equal to x up to 1, and then 1 from 1 to plus infinity. So this is the definition of Lx, the distribution function associated to the Lebesgue, to the uniform measure in 0, 1. And so as we defined for omega in n, q as lambda, q of this set will be L of x if omega is in n. And by construction, Gx is G measurable, n is G measurable. So this means that this function here is equal to that one almost everywhere, and therefore this as a function for a equal to minus infinity x, as a function of omega, this function as a function of omega is G measurable because, well, this function is G measurable as a function of omega, and the set n is also, so we could write this, if you wish, as this is Gx of omega in the set n plus Lx in the set n complement plus Lx in the set n. And this function, it's a function G measurable because the sets n are G measurable, and this is a constant, and this is a function which is also G measurable. Therefore, this function is G measurable. So that proves this second property 2a in the case in which the set A is minus infinity x. Now, by linearity, we can go to a set A which is of the form AB. Right? By writing this set as this set minus another set of the same time, and using that the measure of A minus B is equal to the measure of A minus B, the measure of B if B is contained in A, we can extend this property, the fact that it's G measurable, to these sets, to that set. So this is first step. Then the second step, by using the linearity of the measure, we can extend this property, which is the G measurability. So we first prove this property for these type of sets A. Now we can extend it to this type of sets. The third step is using linearity again to extend to finite unions, disjoint unions. So that will be also G measurable if I take the union of AI, BI, and if I assume, say that BI is smaller than AI plus 1, strictly smaller. So all these sets are, all these intervals are disjoint. Now by using, if this is G measurable for this type of set, by using linearity, it's also G measurable for this type of sets. This forms an algebra of intervals. So my first claim, my fourth claim, is that the set M for which this is G measurable, it's a monotone class. So what I'm saying is that this family of sets A such that this function is G measurable forms a monotone class. I leave it to you to check that this is correct. And then we can use, finally, in the fifth step, the fact that if I have a monotone class which contains an algebra, then it also contains the sigma algebra generated by this algebra, but the sigma algebra generated by this algebra is the Borel sigma algebra. So this proves that indeed, for all A in the Borel sigma algebra, this function is G measurable. And that proves, therefore, this second property of the regular conditional probability, that for all A in F, which in our case it's the Borel sigma algebra, the measure of A as a function of omega is G measurable. So that completes step 3. So in the last step, we proved the measurability, and now it remains to prove this identity. So last step, step 4 in the proof, what we want to prove is that if I take any B in the Borel sigma algebra, then the integral over B of Q omega A dp, that this is equal to the probability of A intersection B. And this is for all A in G. So if we take, this is all A in B, all B in G. Right? So Q, it's defined on B, so for all A Borel subsets, and for all B in the sigma algebra G, we have this identity. So this is what is stated here, and so we have to prove that. So let me fix set B. So we'll prove that step by step on B. First, I claim that this holds if I take A to be a set of the form 0x. So first I claim, so these are the Borel subsets of 0, 1. So let's take this set A 0x, and I claim that this identity holds for all B in G if A is equal to 0x. So let's write the left-hand side. So this is Q omega of 0x. X here, it's larger or equal to 0. Now, since Q, I don't care about omega in n, because n has a measure 0, so I care only about omega when omega belongs to the complement of n. When omega belongs to the complement of n, Q of omega is concentrated in 0, 1, so this is equal to B, Q omega of minus infinity x. Well, because the measure of this set, it's equal to the measure of this set, because Q is concentrated on 0, 1. Now, the measure of the set minus infinity x, it's equal to the distribution function computed at x. So this is the integral of b gx of omega dp. And, well, we are almost there. Now remember that gx is the limit of fy for y decreasing to x. So now I can use the dominated convergence theorem, because f it's bounded by 1, to say that this is equal to the limit as y decrease to x of b f y of omega dp. This is by the definition of gx and from the fact that f it's bounded. And now we can recall that fy is the conditional probability of the set minus infinity y given g. So this is equal to the limit as y decrease to x of the probability of b intersection, so it's closed, so it's minus infinity y. This is by the fact that fy is the conditional probability of this interval given g, and therefore it satisfies this identity for any set b in g. And now by taking the limit of y to x, this is equal to the probability of b intersection minus infinity x, just because this set is decreasing to that one. And finally, well, since p it's a probability in 0, 1, I can rewrite this as the probability of b intersection 0x. Right? And therefore, now if you go back, what we have proved this identity provided A is the set 0x. So this identity, which is 2b, holds indeed if A is the set 0x. And now we will proceed as before, extending this identity to the whole sigma algebra just by using the monotone class theorem. So it's fine if A it's equal to 0x. now it will be fine for all type of intervals AB if now we subtract a set. So we have seen that actually we can. So by here I mean either I take a set AB with A strictly positive and B less or equal than 1, or to a set 0x, which we already proved. And from that we can go to the algebra generated by these sets just by using linearity. So we go from this to this by using linearity, representing a set of this type as the difference of two sets of this type. Now we can go to, by using again linearity, go from a set of this as a finite union of set of this type or that type. So it holds for the algebra. Now we can claim that the family of sets A which satisfies this identity, it's a monotone class. And finally, we can use the monotone class theorem in order to saying that, well, if this class of sets which satisfy this identity, it's a monotone class and contains the algebra, it contains the sigma algebra, but the sigma algebra is the set of Borel sets. So this proves that this identity is satisfied for all set A in B, and this is exactly the property we needed, and therefore this completes the proof of the existence of a regular conditional probability given G, given a sub-sigma algebra G of the Borel sets when the set is 0, 1. So you see, the proof is quite elementary. Use only the fact that we can define a family Fx of conditional probabilities for a dense and countable family of points, and is this dense and countable which permit us to extend and to construct the measure. So you see that in order to prove, to extend this idea to another sets, we need essentially the existence of a dense countable family. And with this, well, I complete these lectures.